Welcome to qnawire.
Okay, so in this problem, we have a man jumping off a platform and then he hits the ground and his knees bend a little bit as he decelerates and then comes to a halt. Um, so that's the little story that goes with this problem. But just for starters, in part A, we will want to know what his final velocity is just straight up due to gravity because he fell from 3 meters, which is kind of a high height. So that's his mass. That's how much he fell or how far he fell. So let's go ahead and calculate that final velocity. All right, so the variable that we know nothing about in this problem is time. So we're going to need to use the kinematics equation that does not involve time. So that's the moment the velocity squared. And in general, this is a positive 2a delta y. So he's just standing there and then jumps off. So his initial velocity is 0 because he begins at rest. So now we can go ahead and isolate the final velocity by taking the square roots of both sides. So we get 2a times delta y. And then square roots are a little funny because you can get a plus or minus, and I'm actually going to take the negative solution to the square roots because he's falling downward and comes downward with that velocity. So that's the reason why there's a negative sign. So we have 2 being multiplied by the acceleration due to gravity, which is negative 9.81. And then his displacement, which is negative 3.1. So the negative signs cancel out. Don't need to worry about imaginary numbers. And then after we take the square root, we get that he ends up falling at a final velocity of negative 7.80 meters per second. Good. And then part B, he then touches the ground and then bends his knees such that his center of mass moves another almost a little more than half a meter, 0.60 meters. And then now the number that we found in the previous part is what we're going to call our initial velocity of negative 7.80 meters per second, because we know that his final velocity when he finally finishes bending his knees, comes to rest, is 0. So over the course of this interaction, we want to know what the acceleration was in order to achieve that. And because there's no mention of time, we're again going to use the same equation, just with slightly different labeling. We have that the final velocity is 0, and other considerations like that. So we go ahead and use this, but this time it's the final velocity that's going to be equal to 0. And then we can isolate for the acceleration, which we now know is going to be negative v naught squared over 2 delta y. Plug in some numbers. So we know that v naught is, negative 7.80 meters per second. We're squaring it anyway, so the negative sign is going to go away. On the bottom, we have a 2, then a negative 0.60. So those minus signs will also cancel out. So we will, not squared. So we will get a positive acceleration, which makes sense because he's, decelerating in the negative direction. So let's, this is bad planning, but we're one line away, so we'll just transcribe it. Plug in those numbers and you to two significant figures, you get positive 51 meters per square second. So kind of a big force he needs to apply. And then we'll wrap it up with part C up here. We draw a free body diagram of what's going on. So he has his weight that's being directed downward, but he's slowing down as he falls. So I'm going to draw the normal force as being a little bit bigger. So that's ultimately the vector that's going to be slowing him down. And then, of course, the net force is going to be equal to the sum of all the forces. So that's just N minus mg. So we can rearrange this to solve for the normal force, which is, I guess, what we're interested in. That's going to be the net force plus mg, if we just add mg to both sides. Newton's second law tells us that the net force is going to also be equal to ma, so we can factor out the m to just get acceleration plus g. And yeah, we can finally use his mass, which we know is 75.0 kilograms, add the acceleration we just found, which is 51 to 9.81. Plug that into a calculator, and two significant figures get 4,500 newtons is what n is equal to. And lastly, we want to know about the normal force to weight ratio, which is going to be the normal force that we just found, divided by that mg. So this is 4,500. Down here is 75 multiplied by 9.81. Plug this all in, and then we get a normal force to weight ratio of 6.2 is how hard he needs to exert.